the first part is very simple. You would trust me. It's called the transportation simplex algorithm because it is based on the simplex method. And it is called transportation because it is to solve the transportation problem. Transportation simplex algorithm. Okay, let's say we have this example where you have 5 rows and 6 columns. And the numbers that you see over there are the costs. The little numbers are the costs. The numbers at the end of the rows are the supply figures. The numbers at the bottom of the columns are the demand figures. And in this case, you can check that the sum of the numbers for the rows equal to the sum of the number for the columns. Otherwise, the problem is inconsistent, we say. So step 1 is the selection of a starting feasible solution. The simplex method starts always with a feasible solution. We do the same thing here. There are 2 methods to find the starting solution. One is called the northwest corner method for obvious reasons. And the other one is called VAM. It's after a guy whose name was Vogel, V-O-G-E-L, maybe in German. Vogel's approximation method, VAM. So we are going to do 2 things, NW and VAM. Let's start with the NW corner method. Okay, here we reason like this. You look at the data, let's put it here. This is not big enough. So let's leave it there. Okay, once you have the table here, then you locate the top corner here, top and left. Okay, so you go to the top and to the left. That's the western corner. Okay. Once you are in here, regardless of the data is represented by the cost. Then you look at the number at the end of the row and the number at the bottom of the column. It says that this row has 150 units, and this row, this column needs 100. Then select the smaller of the 2. It makes sense. So how much can you put in here? The answer is at most as the minimum between 150 and 100. Think about it. You put 150 here, then you violate this. So it's over the minimum. So you select the minimum, and the minimum between 150 and 100 is 100, then you put it in there. When you have put 100 here, then we say you have satisfied, that's the word that we use. You have satisfied the condition for this column, for the one that corresponds to the minimum. Once you locate the NW corner, and you put as much as possible there, which is the minimum between the 2, I call it projections, if you will. This is a projection, or it's a horizontal projection, and this is a vertical projection. The projections, it's my own term, 100 and 150. So the minimum of the 2 projections is the maximum flow that you can put there. And then you satisfy either, sometimes you satisfy both. If the number 100 here and 100 there were the same, if you have the same number here and there, then you satisfy both the row and the column. But typically you satisfy one of the 2. So in this case we satisfy the first column. Look at what we are going to do. Look. You see what I did? I got rid of that column. There is no column 1 anymore. There are columns 2, 3, 4, 5, 6. So we look at the first column, we satisfy this column, and we tell the column, adios amigo. Okay. Then it is not anymore. Then we repeat the same thing. With the remaining table, you look for the NW corner. Even a kid can do this. Okay, and then you get the M2U corner method here. It says select that corner. And then look at the projections. Okay, remember that before we have 150 here, you don't remember it is there. When you put the maximum flow in the M2U corner, then you get rid of one, either row or column, and you have to adjust the other one. The other one, I already took care of 100, so it's still 50 left. So that's what I have there, 50 left. Repeat the procedure. Look at the projections, 50 and 150. So I have satisfied the first row. There's no more first row anymore. You will see. But since I am taking 50 here, this 150 needs to be adjusted to 100. It's pure kinological mind. Tell me it's not. Yeah. And when you do this, think about money. We will be more careful with the money. Think that you are dealing with money. You are not confused. You don't know if the numbers are right. Think that they are money. You know that money is yours. Then you will check your calculations again. Okay? And there is no more row ones, and then you have one there. Good. You see it? Okay, here, this was 150, it went down to 100. Now, the two projections, 100 and 200, I satisfied this one, and this 200 becomes 100. No more column 2. Good. This becomes 100. Good, 100. And you continue like that. You understand this here? Okay, how about that one? You understand that? How about this one? How about this one? You understand that? How about this one? Yes? See, once you are here, okay, you understand this?
Yeah.
Okay.
I didn't understand the 3 yellow.
Okay, I'll tell you what it means, okay. The 3 yellows, okay. When you satisfy this one, 250 and 300, then you put, I'm just doing it fast here, then in this case you put 250, so you get rid of this, okay. But now this is going to be 50, and at the end you have only 50 here, which is for this one, and you have 200 here and 250 there, then you put 200. So the last two are automatically are readily available. So we'll look at what we did. That's what we did. The solution tends to be along this area like this, by design. That's the initial solution.
So what does the M represent?
I was going to talk about that. The M is the same as the big M in linear programming. Say every time that it is not possible to ship anything from one source to a terminal, then you define the cost equal to infinity. And in here I would represent it by a big M. So it says here that it is not possible to ship anything from supply center 4 to demand center 6, then the cost is M. And the problem will make sure that you don't have that one there. It will be 0 in an optimal solution. Okay, raise your hand if this is clear to you. Crystal clear.
So
You see it?
Get
Get it there, okay. Move your hand, you have your mind. If you raise your hand, your mind says, okay, you raise your hand, you will do it. You don't raise your hand, the mind says, no, we don't want to do it, then we won't do it. It's pure psychology.
Could you explain why you had to adjust on the first iteration?
Yeah.
than the others?
Yeah, I adjust that in every iteration, not on the first one. Everyone I did shows.
Okay, so here the minimum was 100.
And then you have, then this becomes 100 the next day.
Okay.
Okay, we have this. Okay, the solution, the value of the objective function, the policy cost is 40,950. How do you do that? Multiply the flows by the cost. So these are yellow entries. They look green to me here. But blame it on the projector. So you multiply the flow by the cost, and at the end you get 40,950. That's not an optimal solution. In all probability, it's a feasible solution. Okay, the other way to get an initial solution is called Vogel's approximation method. Yes.
So, are you saying you take 100 times 19 plus 50 times 49 plus
Yes.
30
Yes.
times 100 plus 28 times
Yes,
100?
yes. You do it like this, like this, like this, like this, like
You
this.
just add them all up?
You add them all up.
Okay.
And
Yeah.
would we know to put an M in that spot at this point, or just put that in?
Okay, M, the procedure will stay. In this case, I didn't choose the M, so there was no problem. But if you had an M, for example, instead of the 19, let's say here, okay, let's say I have an M here. Okay, this is the M2U corner method. So I should use this, but I know when I use one that has an M card, then I will use either this one or this one. Just take the one that is next to the one. And continue the same procedure, and in the next one, I will consider the M2U corner as much as possible every time. So you avoid M's by moving to the right or underneath a little bit.
But we wouldn't have to put that M in, it's already in the problem, I guess. Okay.
Because part of the statement is that it is not possible to go from 4 to 6.
Okay.
That's part of the problem. It's not possible to go from 4 to 6. Then you define the cost equal to 6 to M.
At the end of this, all you get is it is a basic solution, but not a basic feasible solution, but not the optimal basic solution.
Yeah, that's correct. See, this is a very easy thing. So in all probability, it's not an optimal solution. The next one is another procedure. It's a smarter procedure. Smarter procedures demand a little bit extra work. You just do a little bit extra work, but the procedure is smarter than the one before, so it will give you a better solution. You will see. It's called Vogel's approximation method, after the person that developed the procedure. Okay. The idea is the following thing. If you look at the first row, what is the lowest cost in the first row? It's 19. Okay. But let's say I don't want to use the lowest cost. I'm going to use the next to the lowest cost. Okay. So for the row, the next one should be this one. You agree with that?
Why do you choose that one, sir?
No, we are assuming that if you don't choose the lowest one, but you choose the next to the lowest one, then there is a penalty. The penalty is the extra cost. So the procedure capitalizes on those penalties. So for every row and for every column, we are going to find penalties. So I'm elaborating that here. The penalty values for the sources and the terminals are going to be written in parentheses. For example, here, okay, 24, why? Because if I don't use 19, the next one will be 43, so there is a penalty of 24. The penalty is for not having used the lowest cost. Okay, for the other one is 8, and check this, and this. Check, for example, this one, look. there is a 20 here. Well, there is another 20 there, so there is no penalty. I don't choose this one, but I can choose this one. And this one, the lowest one is 20. The lowest one doesn't have to be in the first column. In here, some of them are in the first column, but that's irrelevant. Okay. So raise your hand if you understand this. That's called penalties for the sources or the rows. Similarly, let's look at penalties for the columns. This is 0 because you have 19 and 19. Now this is 22 and the next one is 32, that's a 10 and so on. Those are penalties for rows and columns. And you put it in parentheses. To the left of the rows and to the top of the columns. Okay, then you scan all the penalties. This is the logic of the procedure. Scan all the penalties. Identify the largest one. This one is the largest one, 24. I say, okay, to avoid that penalty, I'm going to choose the lowest cost. That's the whole idea. So calculate penalties, identify the largest one, and avoid it. And to avoid that one, then we are going to choose the lowest cost. This is 19. Okay? And from this point on, it continues the same as before. You have the projections, 150 and 100. So you can put at most 100 there. Once you have the row or column with the largest penalty, then identify the lowest cost in that row or in that column and put as much row as possible there. That is 100.
So the
Then-
largest penalty will always have the lowest cost? Is that
You think?
correct? The largest penalty, that box will have the lowest cost?
Yes.
Okay.
See, once you have the row or column with the largest penalty, select the lowest cost in that row or in that column, whatever it happens to be, and put as much flow as possible. And in this case, I am going to put as much flow as possible. It's the minimum between 150 and 100, so it's 100. And now I'm going to get rid of this column. Look, I'm going to leave it blank, so you see that I got rid of that. Then I adjusted this number to 50 and repeat the procedure. Okay, for the remaining portion of the table, find penalties for the rows and penalties for the columns. It's all the same, very systematic.
So your penalties change each time you get rid of one?
You adjust, yes, the penalties are going to change. May change, you know, it will change in many cases. Okay, so remember I have a 50 here. Because see, I don't have now these entries, so I have to recalculate penalties. I get this one for the columns and this one for the rows. Look, that's the maximum penalty. If there is a tie, you break the tie arbitrarily, choose either one. Like for example, you have a 10 here and a 10 there, I chose this one. You may think that I chose the penalty here. I chose this one because the 49 is less than 55. That is not super sound thinking, because at the end, if I have to, I might work less or even more. I don't know at this time what will happen, but one of the two will be safe to choose. Okay. Usually these problems, as linear problem models, have multiple optimal solutions. And that's when you have ties like this, that's an indication that you are going to have multiple optimal solutions. Okay? Then, look, select the lowest cost, 150. 22, 150, 150 here and 350 there. I'm gonna select 150, then the next one is 200, yes.
But the 150 correlates with that entire column, so how did you pick the row?
No, I selected the column, I selected this column.
Right, so how'd you pick the row?
That's
Okay,
22.
because I scanned the
It
cost.
just defaults.
49, 37, 33,
It
22.
just defaults across 22.
This is the lowest cost. So I need to put as much flow as possible in here. So what is the projectors?
Got it.
Projector?
Okay.
350 and 150. So I put 150. This one becomes 200. I have satisfied the two columns. And I have modified this one. Look. Look at this number. 200. Repeat the same thing. These are the penalties for the row, penalties for the columns. Okay, get the largest penalty. To be this is the lowest penalty. Look. Scan the cost. This is the lowest cost. Put 200 and 250. So this becomes 50, and now you have satisfied this. Same thing, get the largest penalty, get the lowest cost. Yeah. Now, look at an interesting thing here. 250 and 250, I got rid of those two. Now I have a little bit of a problem, you will see later on. Don't worry about it, but I have a little bit of a problem. I can show you what problem it is. Then I have this, and that, and this, and then this, and now I have that. Repeat the thing here, and there, here, there. Now I don't need this, and this is 50. And I have that one. That's 5. The only one, and that's 50. That then I can put, the last two are always easy to do. When you go through this, you have this. Now notice that these are distributed everywhere, not like the other ones that were along the main diagonal. And look at the price that you have get. This is the reward. The other one was 40,000 some. This is 39,300. Yes.
If you go back a slide,
Yes.
is there ever gonna be a time where you're not
Yeah,
gonna
but
have,
this is misbehaving again.
is there ever gonna be a time where you have your column and your rows constraints that won't add up, like your 50/50 plus 2?
No, it cannot happen.
So it won't ever happen, so
No,
if you
no.
start having to do something wrong.
Yes.
All right.
Yes, please. So, look, I'm not doing anything. Why don't you check it? I think there's something wrong with it.
The cord has a short end.
Let me see it for a second.
Yeah, do it.
Turn it off first before we work.
I have a powerful voice. I could have been a preacher. No.
Where is this?
That time that we were able to get rid of both the row and column because they both had 250, the same values,
Yeah.
will that happen with the northwest method too?
It could happen too.
Okay, and you would get rid of both of those
Yeah.
as well?
Yes. Okay, now, 39,300. And step 2, that was step 1. Is it possible to continue here, or that would take the sound away from the video?
No, it just amplifies, the mic's actually on the camera.
Okay, You want me to get closer?
Talk towards the camera.
Hey, guys, this is the Almighty calling you. Anyway, step 2, identification of the non-basic route to be brought into the basis. Step number 2, identification of the non-basic route to be brought into the basis. Look at what we have now. Now, what do we mean by basis? Everything that is highlighted, that has a background highlighted in some color, that is a set of basic routes. We call it basic routes, to use the transportation terminology. And it has 1, 2, 3, 4, 5, 6, 7, 8, 9. But we should have 5 plus 6, 11 minus 1 is 10. See, I have a problem. When I got rid of 2 at the same time, then the number of basic solutions should have been n plus n minus 1, but I got rid of 2 at the same time. Now I have only 1, 2, 3, 4, 5, 6, 7, 8, 9. So I do, there's a trick. It's a very simple trick here. But I want to, so look, everything is the simplest method. Everything that is color here is a basic variable. Everything that is not colored is a non-basic variable, except that I have to use one cell and color it, because I need to have n plus n minus 1. And once I choose that one and I color it, then everything that is not colored is non-basic. And the procedure says, identification of the non-basic route to be brought into the basis. Good, thank you. You can put it where you think is best. Now we are cooking with gas. Okay, once we determine, this is based on the simplings. Once we determine the route which enters the basis, we can find the pattern of alterations of the basic routes when the flow on the entering route is increased from 0. In other words, if we are going to identify an empty cell and we are going to put flow there, then we need to do something to the existing flows, because otherwise, if we add flow and we don't do anything, we are violating the demand and supply conditions. So we need to do something, and we need to identify how the flows that I have on the table can be altered to establish the feasibility of the solution. Now, once you identify the alterations, that pattern of alterations, they have a pretty interesting sentence or name for that. It's called a stepping stone path. You are familiar with stepping stone paths. Okay. So here we are going to do almost the same thing. When a route increases its flow, this is terminology, because there are some routes or cells. Every cell is a route. When you increase the flow on a cell, then another one has to reduce the flow. You cannot just increase and leave it like that, because you will violate feasibility. So if you increase the flow and another one reduces the flow, then those that increase the flow are called recipient routes, and those that decrease their flows are called donor routes, because the ones that decrease the flow to give it to other routes. An example is very easy to see. A basic solution has m plus n minus 1 variables at positive levels. Sometimes, like in this example, the number of basic variables is less than m plus n minus 1. Note that we have 9 instead of 10. Then we must add one variable with, this is the trick, an infinitesimal value. Let's say you got a major, a minor in mathematics. So what is an infinitesimal value? What do you think an infinitesimal value is? Minor in math And it's Spanish, right?
So finite, so it doesn't, so it's not a finite value.
No, all I wanted to ask is, what is the definition of infinitesimal?
Tiny.
It's a quantity that in the limit is equal to zero, but it never reaches zero. It's as close as you want to zero, but never zero. That's an infinitesimal value.
Sorry, we didn't do that.
Can you repeat? We didn't hear you.
This thing is not working. Tell Carla and Ruby, don't you think that Carla and Ruby should go tell us and give us a new one?
Yeah.
Yes. Okay. Then we gladly do it. We ask, I'm sure. Okay. I was saying that an infinitesimal is a quantity. I'm going to represent it by epsilon, like in math. Epsilon represents a quantity that is as close as zero as you want it to be. For example, 10 to the minus 100. That's pretty small. Or if you want it bigger than that, then 10 to the minus 1 million. That's fine with me, because 1 divided by 10 to the power 1 million is not zero. But it's darn close to zero. Okay? That's what I was saying, and we're going to represent it by epsilon. Okay, where do you put that epsilon? There are several choices. Okay, the answer to that question is you put the epsilon in an independent cell. I'll explain what I mean by that. So the cell would be an independent cell. Okay, and I'll tell you what it means with the example. Okay, let's look at that one. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. I need a number 10. Okay, let's say I put it there or there. Let's see what is the difference between the two things. Okay. In the second one, the bottom one, if you understand the bottom one, then you understand the top. If you put it in here, then you can go to another basic route. Look, you cannot follow a path that doesn't have basic routes. It's only following basic routes in the corners. In every corner of the path, you must have a basic route. You may have basic routes along the line, and it's fine if they are there, but at the corners, you must have a basic route. You cannot make a turn if you don't have a basic route in this path. You may have another one here, but I'm not going to turn there, so that's no problem. In here, you don't have it, but I'm telling you, you could have one there. So start here and move to the right and see if there is one. Yeah, you will use this one. Make the turn. Go to down this, see if there is a possibility of making a turn. Yes. Go like that, and another possibility, and here there is another possibility. And if you can start at the route, at the cell where you want the epsilon, and end up at the same cell, don't use it, because that's not an independent cell. So don't use this one. Here, try to do what I said. Look, start here and try to get another basic route that will serve as a corner. Okay, this one is the only one. Okay, use it as a corner. Then you can use it here. Okay, use that as a corner. Here, you can use this one. Try to use it as a corner here, but there is nothing, there's no way you can go here. So put it, there are several solutions, several possibilities. That's fine. This is not fine. This is fine too. Try this one, and you will see that that is also a good one. Because you start here, but you cannot get back to the.
So that would be
So those are independent cells.
Okay, now.
The top ones are examples of independent cells. The bottom one is an example of a cell that is not independent.
Now, why can't we use the bottom one?
Because in the bottom one, you can start at the cell, and then you can come back to the same cell.
I mean, could we, okay, so you're trying to get out of that grid, right?
I want to get an
Kind of work
epsilon.
your way out.
Yes.
Okay.
See, I want to put an epsilon in that cell where I cannot go back to it, using the basic solutions as corners of my path.
But you could, there's a couple of other places you could.
Yes,
do
yes,
that.
there
Okay.
are, yeah. There are several possibilities, but any possibility will work. Any one will work. So I'm gonna use this one. Look, that's another one. So you can check. Well, I'm gonna use this one. That's the one, and now I count. I will continue using epsilon instead of a number, but this epsilon is very, very close to zero. Okay. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm in good shape. Now I can go into the calculation of the dual values. If you don't have m plus n minus 1 basic solutions, you cannot calculate the dual values. Because the dual values, we are going to use equations to calculate the dual values, but the equations are very trivial equations, can be solved in the head. I'll show you how to do that.
Dr. Steve,
Look, I have, yes,
Since the, since epsilon is a limit of 0, we don't have to put those, make any adjustments like that 250 minus
no,
epsilon or anything like
because
that.
it's as close as you want it to be zero. Not zero, but as close. Yes, good question. Okay, so look, I colored that epsilon in red, but it's the same as the other. So count basic cells. I should have 1, 2, 3, 4, 5, 5 plus 6, 11 minus 1, 10. I should have 10. If I have 10, I am in good shape. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't want to make this problem as necessarily complicated. They have computer programs that deal with that. But you might need 2 epsilons. So that's fine. You could 2 epsilons and so on. But in this project, you need only 1 epsilon. And I'm not going to give you a problem where you will need many epsilons, only 1. So you can practice because all this is done with a computer.
So
Okay, now, yes.
what made those basic cells?
Those are cells where you have answers, flows. Okay, so those are the basic cells, are the routes with the flows.
So how did you know you needed 10?
I did 1 because you should have m plus n minus 1. M plus n minus 1 is equal to 10, and I have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is the 10.
How do you know n plus n equals 10?
Well, number of rows is m, and number of columns is n. So it's given to you by the data. Number of rows, m. Number of columns, n. So number of rows plus number of columns minus 1. Minus 1.
Oh, yeah, sorry.
M plus n minus 1. Okay.
Gotcha.
Okay, now look at this. We have spent quite a bit of time with this one. For every basic cell, this number is the value that you would have in the objective function row of the simplex tableaus. This is the one that you get for any basic variable. It's 0, because remember that every basic variable has a 0 in the objective function line at any iteration, because it's the top 0 for the column that contributes to the formation of the identity matrix. So I know that every time I have a dot here, I don't need the numbers themselves, the values of x. Look. I don't need this 50, 200. At this time, I don't need it. I just put it like this. I have a feasible solution here. And I know that this one, r plus k plus c, must be equal to 0 for every basic cell. So where you have a dot, you have to have r plus k plus c equals 0. Furthermore, remember that r and k are unrestricted, so they can take any value. They can be negative, they can be positive, they are unrestricted. Then we always start with this first row, always. Look at the way we are going to do it. Start with this row. Set always the first one, r equal 1 equals 0, always. Set equal to 0. And now scan the dots on the row. Here, look, it's very easy. Look, 0, plus 19 is 19. But you have to have 0 plus 19, 0 is 0, plus 19 plus k equals 0. Then what do I need for k to have 0 plus 19 plus k equals 0? So k needs to be equal to minus 19. Do you agree with that? Let's put it like that. Look, it's like a game. Now that there is nothing I can, no more dots here, but I have more dots here. So now I have 0 here. I go like this. 0 plus 47, I need minus 47, and that's K5. You agree with that? Look. That's not minus 19. Now this one is minus 47 because it's 0 plus 47 is minus 47 equals 0. So K sub 5 equals minus 47. Now that I have this one, then I scan more dots. I have one here and one here. Okay, with this one, I can get this R. Then it says minus 47 plus 30 is minus 17. Then R2 is 17. It's like a game. Very simple game. Okay. Now I have this. Okay. Is minus 47 plus 70 is what? Minus 23. R3 equals minus 23. So minus 47 plus 70 is 23, minus 23 equals 0. With this minus 23, then I can get this k here and this k there. And then I get, yes,
You had minus 47,
yes,
then you
I have minus 47.
add 30.
So it is minus 17, then R2 must equal to 17 because R plus K plus equals 0.
Okay.
Now check that, look, 17 and 30, 47, minus 47, 0. And then do it like this, for this one, minus 23. And now I can get this and this one is minus 17.
C is this value.
You follow what I'm doing? Yes? Okay, like this, look. What is the next one here? Tell me, what do you have in there?
Minus 12.
Say it.
Minus 12.
Minus 23 plus 35,
12.
that's 12.
Minus 12.
So it's minus 12. Okay? You continue like that. With this one now, I can use this one. Minus 17 and 30 is 13 minus 13. And with this one, I can get this one, minus 9. Okay? And then, now that I have this one, look, this is the epsilon. If I had not had an epsilon here, I would get stuck. I would not have been able to move beyond this point. So the epsilon now is going to perform its role. And it's allowing me to do this, and with this, I can get that one and get that one. I have all my dual values. Then, since I have the dual values, remember, R plus K plus Cij are the values of the non-basic variables too. These are 0 because they are basic variables. But the same calculation is done for the non-basic variables as well. And then for all the others, for example, look at this, the one where I have here, 19, is 0 plus 49 minus 9 is 40. So that's the value that it will have on the Z, on the objective function row at the top of the tableau at any iteration. It will have a 40. Let's do one here. That's 40. So the value of the Zj is Zij minus Cij value for the simplex is equal to minus 40. It's what I was doing here. Look, I'm glad I didn't erase it here. I put Ri plus Kj plus Cij. That's the value. If you were going to solve this problem with the simplex method, that's the value that you will get on the tableau at every iteration. So
Where are we
No.
getting CJ? Where are we getting CJ from?
Excuse me.
Where are you getting CJ from?
Okay, is equal to this, R plus
R1
K
is
plus.
zero, right, R1 is zero.
Zero where you have that. For the other one, you are going to calculate. Because like, let's take this one here. 49, I want to calculate this one, R plus K plus C, but it's not going to be zero because these are not basic variables, these white ones are not basic.
Well, but for that first one, the first basic variable.
Which one do you think this one?
It's not equal to zero because it's, so you don't
Because
use
it's
that formula.
non-basic.
Okay,
Yeah.
okay. So we don't use that formula.
We calculate the value, but it doesn't have to be equal to zero because that formula was done to solve for dual values, and now you have the dual values already.
Well, how did you get 40?
40 is this, look, 0
Yep.
plus 49 minus 9. It's the same calculation as this one, but it doesn't have to be equal to 0. So you add, for this one you add R plus K plus Cij, R plus K plus Cij. It will not be 0, it may happen to be equal to 0, but it will not be 0. That's 40, you put it there. Okay, how about this one? Look, 0 plus 43 minus 6 is equal to 37. And those are the value. I could write a simplex tableau with the stuff that I'm getting right now. I could. But we are not going to do that. The idea is to avoid the simplex method. So you have this one, and then now find this one. Look, 0 plus 55 minus 17 is equal to 38. You have that one. And I'm gonna do everything else at once. Okay, one more time. 41. 0 minus 12 plus 53, 41. And now here, look, I did everything. Here, now this is the, let's remember when we're doing the simplest. In the simplest, you will look for the lowest number, remember? You remember that you look for the lowest number? Okay, where is the lowest number? Scan the quarter circle values. 40, 37, 38, 41, 18, 45, 39, 42, 43, minus 23, 1, 0, minus 35. It looks, this is the winner. Look. That becomes the entering variable. That becomes the entering variable. Okay. Look at what we have. Look at the dots. Remember, this is the one I'm going to include here. These are the others. That's the one I have, my 35. These are the others. Yeah.
On the previous slide, you're missing a value for R5K6. Is that this guy?
This one?
No, the next one.
Oh, I should have it there. I don't know if I. Yeah, I should put this one. Yeah, I'm sorry. Send me an email. Okay, I need an email from you and an email from you. And then if you don't send me an email, I probably will forget it because remember I'm going to have a Corona beer tomorrow. See, I'm nearly perfect. Because so here I should have minus 23 plus 41 minus 12 and put it in here. It's not going to be the one I have. In the reading guide, I may have it. I'm not sure.
It's in the reading guide.
Yeah, it's in the reading guide. See, the reason is I develop my reading guide first, and then I put the PowerPoint. But when I developed my reading guide, I forgot the summation thing, the transportation problem that I asked you to remind me. Okay, here, look.
That's what we have. And then the following thing is called a path of stepping ascent. I mean, a path of stepping stone. It's a path of the stepping stone path. So that means you are going to, let's say that you are on this path and you are going to go jump to stepping stone so that you don't want to get wet, okay? So here you are there. And these are the stepping stones there. You want to find the path. Find one. This is it, see? You could have another one, but this is one. So the rule is that you have to have a stepping stone at the corners of your path. And here is to go back. You have to go back. It's the opposite of the concept of independent cells when we're trying to put the epsilon. Now we want to find the path because we are going to change flows. Flow alterations follow a closed stepping stone path with basic cells at each corner. So this doesn't matter, this doesn't matter, it could be like that. Now, this is a general picture. I'm going to show you a picture for our problem in a minute. This is what we have for our problem. Look. -35, then this, then you could do this. Okay, look. I am going to go like this. The stepping stone path goes like this. This square here. See, I'm showing there how I am going to get out, start here and end up here, following a path that has stepping stones in the corner. Okay, I need flow here. Okay, I need there. Okay. Here, you have 300 and 350. And here, 250 and 300. Okay. Okay, remember that. This is 300 and 350.